come back to this second half of this lecture. In the earlier part we have seen Hilbert basis theorem and some of its consequences. And now I want to give some more consequences of Hilbert basis theorem, but firstly I will make one all right. So, this is like linear algebra. Linear algebra you would have you were studying linear operators on a finite dimensional vector spaces. This will be more general. Now I want to do this for a more general setup where modules are over Noetherian ring, or at least modules are finitely generated over arbitrary commutative rings. So, I want to prove theorem like this. For example, this was very easy to prove in case we were studying vector spaces. So, this is a theorem. So, here let V be a Noetherian module over an arbitrary ring A. And again I want to remind you, whenever we say ring, it is always a commutative for us. And F is an endomorphism of V, and A V. Again these are called endomorphism, they are A module homomorphism from A to A V to V. So, this is also same as hom A V V, homomorphism of A modules from V to V. Then the following are equivalent. So, proof, no, not proof, the statements. What are the statements? 1, F is actually an automorphism, not AV. 2, F is surjective. Remember, you would have seen in a linear algebra course that if you have a finite dimensional vector space, then the linear operator on that V is surjective if and only bijective if and only injective. So, this is analogous of those statements over an arbitrary ring, but the module should be Noetherian. And in the corollary I will deduce, you do not have to assume really a module is Noetherian, you just have to assume that it is finitely generated module. Okay, so, we will do that in a corollary. So, third statement, F has a right inverse. That is, there exists G, another endomorphism of V, such that F compose G is identity on V. I will explain this, why am I using this language. And fourth, F has a left inverse. That is, there exists another endomorphism H such that HF equal to identity on V, and when I say HF, that is H compose F. Now, before I go to the proof about this language, so we are working in this. So, this is I would write this as a remark. See, this end AV is a ring, not commutative, not necessarily commutative, with addition of obvious addition pointwise, and multiplication is composition. So, this is a ring, and this ring is very important to study in representation theory, for instance. And now, because this is not commutative, left inverse and right inverse, these elements may not be invertible, and somebody may be left invertible, but may not be right invertible, and all these things will crop up. This is precisely non-commutative algebra, but only for this ring is more interesting. Arbitrary non-commutative algebra is not interesting for us, at least. So, this is right inverse in that sense. This is, there is a right, on the right side there is a G, so that it is inverse. This is a left inverse in that sense. Okay. So, that was one, and now let us prove. First of all, I will show you that, so proof. I will write here, it is enough to prove that, enough to prove the following statement. That under the given assumption, that means our assumption is a V is a Noetherian modulo or a arbitrary commutative ring, that every surjective homomorphism is bijective. Every surjective A module homomorphism from V to V is bijective. Let me show you why is it enough. So, this, if I prove this statement every surjective homomorphism is bijective, then I would establish the equivalence of 1 if and only if 2 if and only if 3. So, let us see how. So, first of all, 1 implies 2 is trivial, because 1 says it is automorphism, therefore bijective and therefore surjective. So, 1 implies 2 is okay, and this statement which I stated above, every surjective homomorphism is bijective, that we are assuming that we have proved, then that implies 1 also. And how 3 implies 1 or 3 implies 2, 3 equivalence of the. So, look here 3. There is a G such that if OG is identity V is surjective, but once identity V is surjective, then this F is also surjective, it is clear from this. So, right inverse implies surjectivity. So, this 3 will definitely imply 2, and 2 implies 1 already we know, and 1 implies 2, 2 implies 3 is also clear. So, all these equivalences is clear from the above statement, above assertion, which we will prove. All right. And now how to connect 4 with 1? But you see 4 says there is H like this, but now this will prove that this means that H is surjective. But once H is surjective, we have already proved equivalence of 1, 2, 3, then H will be bijective and the inverse of H will be F. So, I will not say, I will not write much, but for 4, so let us not write much. So, it is enough to prove that every surjective module homomorphism is bijective. So, that let us write it as a lemma. So, lemma let A be any commutative ring any commutative ring, and F from V to V is a surjective A module homomorphism of a Noetherian A module V. Then F is bijective. This is very simple, almost it follows from the definition. So, proof. We want to we have given it is surjective and we want to prove it is bijective, that means we want to prove it is injective. So, to prove F is injective, that is kernel of F is 0. Injectivity is equivalent to proving the kernel of F is 0. We consider the powers of F, F power I. F power I means what? For I in natural numbers, F power I means F compose F I times. And these are also endomorphisms. And if F is surjective, F power I is also surjective. Since F is surjective, that is given to us. And now we consider their kernels. So, we will put Vi equal to kernel of Fi, F power I. Then it is obviously Vi is contained in Vi plus 1 for all I bigger or equal to 1, for all I in n. This is clear, because if somebody is here, that means F power I is 0, then F power I plus 1, which is composed of F with F power I, that is also 0. So, this is clear. So, we have an ascending chain of submodules of V. So, since V is Noetherian, there exists natural number n in n such that Vn equal to Vn plus 1, and then all the way they are equal. So, now we will prove that kernel is 0. So, let x belong to the kernel of F. I want to prove F is 0. All right. So, this is contained obviously in V, but we have given that F is surjective, therefore, Fn's are surjective, and therefore, I have given this x. So, Fn is from V to V again, this is surjective, and there is x given here. So, there must be y here which goes to this. So, that is we have written x equal to f power n of y. But then fx is 0, we know kernel x is in the kernel, so fx is 0. On the other hand, this x is f power n y, so this is f of f power n y, which is f power n plus 1 y, which is 0. So, that is y belongs to kernel of f power n plus 1, which is Vn plus 1, but this is Vn, which is the kernel of f power n. So, that means y belongs to kernel of f power n, that is when I apply f n to y, it becomes 0, 0 equal to f power n y. But what is f power n y? That is x. So, done. So, we have proved that kernel f is 0, that means it is injective. So, we have proved the lemma. And remember, we have only used the fact that V is Noetherian, and that means that every ascending chain of submodules of V should become stationary after some time. This is a definition of Noetherian module. Now, I want to write a corollary where I do not want to assume in the above. So, I will show you. In the theorem, see here, I have said Noetherian module over arbitrary commutative ring. Now, I want to drop that and just want to say that finitely generated module over a commutative ring. So, the thing I want to prove is the same theorem will be proved if I proved the corresponding statement by dropping the assumption Noetherian and just assuming finitely generated. So, this does not work so easily. So, the replacement lemma is the following. So, this lemma is more general lemma, but obviously I will reduce to the earlier lemma. So, what now? We have, let V be a finite module over an arbitrary commutative ring A. Then every surjective A module homomorphism F from V to V is bijective. So, proof. Now, we do not have Noetherianness because we know only finite module. If the ring were Noetherian, then we have studied finite modules over a Noetherian ring and they are Noetherian, and therefore, we can apply the earlier lemma. So, we have to, from this situation, somehow we have to come down to Noetherian ring, and that is where I will use Hilbert basis theorem. Okay, so we have given its finite module, that means it's as a module it is finitely generated. So, suppose V is generated by n elements x1 to xn over A. So, our standard notation Ax1 plus 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 Axn, where x1 to xn is a generating system for V, is a generating system for V, and we have given this f. So, that means I have given f of xj's. So, f of xj's for any j from 1 to n, this is again an element here. So, that means these guys I can write in A linear combinations of the x1 to xn again. So, this I can write it again and the summation. Now, summation is running over I from 1 to n Aij xi. for some Aij in A. I can always write like that because V is finitely generated. And what is the surjectivity means now? It's given surjective. Surjectivity means that since F is surjective, every element xi is here, so it is image of somebody. So therefore I can write xi equal to summation bji f of xj. J is 1 to n. Because it is surjective, V is generated by f of x1, f of xn. Image of a generating set is a generating set. So therefore xi, this I can write it for every I is from 1 to n. And what do we want to prove? We want to prove that kernel is 0. We want to prove that kernel of f is 0. So let x belong to the kernel, and I will write here to prove x is 0. That is what our aim is. Well, x is in the kernel, it is in V, therefore in any case x has expression of the type summation I is from 1 to n Ci xi, where Ci's are elements in A for all I from 1 to n, and here also I should have said bji, they are elements in A for all I j. Now what you see, look at this data involves these Aij's, Bji's and these Ci's. So obvious thing to do is, so let A prime be the subalgebra of A over Z. See, every ring A is a Z algebra in a unique way. There is no other algebra structure on a ring of a Z algebra because there exists a unique ring homomorphism from Z to A. These are denoted by chi A. Namely 1 goes to 1 of A, and this dictates everything if you want a ring homomorphism. And therefore as an algebra over Z, every ring is an algebra over Z is in a unique way. So take that Z algebra structure, there is only one, and generate a subalgebra over Z. So my notation is this, by the elements Aij's, Bji's and Ci's. This is a subalgebra, sub Z algebra of A generated by Aij, Bji and Ci for all. So they are anyway finitely many elements. So it's this A prime is a finite Z algebra of finite type. is a Z algebra of finite type. Therefore, A prime is Noetherian. By HBT or corollary, maybe by corollary to HBT, corollary, some one of the corollary. Finite type algebras over a Noetherian ring are Noetherian. That is the corollary I am using. So, it is Noetherian. And now this V, I am considering V as a modulo over A prime or V prime. V prime is a module generated over A prime by the same generating set. So, this is A prime x1 plus A prime xn. This is a sub of Ax1 plus Axn, which is V. So, I am forgetting this V and concentrating on this V prime. Now, V prime is finite A prime module. Finite means finitely generated. Therefore, by earlier results, by earlier lectures, we have proved finite modules or Noetherian rings are Noetherian. Therefore, V prime is a Noetherian A prime module. And what happened to that F? Now, F still makes sense. F is from V prime to V prime. Where do the xi's go? F of xi's. If I restrict this V, this F, so better to write like this. This F is the restriction of F to V prime. I am using the same notation. So, that means what? So, okay, let me write it F prime here. So, F prime of any F prime of any x equal to F of x for all x in V prime. So, it is a module, it is clear that it is a module homomorphism because original F was a module homomorphism. So, F prime is also a module homomorphism and this F prime is also surjective. First of all, F prime belongs to the end, that is clear. F prime is surjective is also clear, since this I need to only prove that all the generating system x1 to xn of V prime is also in the image, but that is also clear because we have written xj's as summation aij xi, I is from 1 to n, this and these aij's are actually in A prime. Therefore, this makes sense. So, it is surjective. Also, this makes sense and also surjectivity makes sense because xi we have also written it as bji xj, j is from 1 to n. So, this means also it is surjective because these are in A prime. So, this is surjective. This makes sense because it is xi going to this. So, it is indeed a surjective endomorphism of the module. This is over A prime, I should say. And also what do you know then? Then obviously then by the earlier lemma this F prime has to be injective. So, this implies F prime is injective by earlier lemma. And also what is clear? this x var, the x I have chosen, we have fixed an element x in the kernel and we wanted to prove it is 0, but that x, what was that x? I just want to show you that. See, we wanted to prove this, we have fixed x which is 0, and this x we have written in the linear combination of, this is Ci. Let me make it clearer here. This is Ci and the Ci also we have added in that A prime. This Ci also we have added in that A prime. Therefore, x is also there in V prime, x is in which was in the kernel which was fixed, that is also belongs to V prime, and that also belongs actually to the, because f prime is a restriction of f, this is also equal to kernel of, so I should write here this, so that implies x belong to the kernel of f prime and therefore x is 0, and that ends the proof. So, we have proved that, and now once I proved this lemma which is a replacement for this which was used in this theorem. Now, in this theorem do not use just Noetherian, just it finite is enough, and instead of this statement you use the second lemma, and therefore, we prove that this theorem is valid for, I will correct here. So, instead of this assumption Noetherian, just, or I will say respectively finite. Then the same theorem is true, and the next time we will now interchange the roles for injective and bijective, and here we use Noetherian, and obviously that time we will have to use Artinian. So, the Artinian and Noetherians are dual to each other. So, like therefore, surjectivity and injectivity will be dual to each other and so on. So, that proves this is very important, because I will show you the use of this sometime, and also I want to write more general statements in commutative algebra, obviously connected to the modules or commutative rings, and in particular finite modules or commutative rings. So, with this I will stop this and continue it in the next time. Thank you very much.